Hello, this is BurakGunay, and it is the first homework of secure software development. For this homework, I've decided to do further analysis on Heartbleed. And as you mentioned, I found the affiliation that you have with the Heartbleed bug, which I'll be sharing throughout the slides. And also, as you can see here on the right, here's an XKCD comic that I found that really explains well the attack in a simple manner. Okay, to give a little background on how this attack came to be, we first need to talk about encryption. So basically, encryption is the way that servers use a security to prevent man-in-the-middle attacks from occurring. What that is let's say me, the client, is trying to reach you, the server, and then there could be someone in the middle intercepting the messages and then reading secure information that should not be read at all. And to prevent this, there's a thing called public-private key pair. And what it does is, let's say I want to send you my password. I encrypt that message first, which gets turned into gibberish. So even if an attacker intercepts it, they can't make sense out of that. And then when you end up receiving it, then you decrypt it with the corresponding key pair. So then the message can reach you securely. So a popular way to achieve encryption is done with using OpenSSL. So the OpenSSL details and then how this attack came to be. To first off, right off the bat, there is no problem stemming from the SSL protocol itself, but there was a problem with the OpenSSL code. And the culprit here is a thing called the heartbeat feature. And what it is a client can send a unique message and then wants the server to return the same message. So on the top here on the image, you can see this is what a normal usage would look like. It will say, server, send me this 4-letter word if you're there, bird. And then the server responds back with bird. And this is quite useful because the server might be sleeping or it might be unresponsive too. The problem here is the OpenSSL trusted the user to send the size of the message. What it is we can see an example of the malicious user here. It says, server, send me this 500-letter word if you're there, bird, which the server responds with bird, and then a lot of confidential information about various users or just private keys, many other things too. And then the malicious users found a way to lie about the size of the message to extract confidential information from the server. So here's how an example attack would have played out. Here, again, the culprit is over here. It's the heartbeat input. And then the part that is start is when the malicious user lies about the size of the message. I'm pretty sure this slide looks familiar to you. I've taken this from one of your presentations that I found online. And here it shows the parts that are at fault with the source code. So on the first red line, we can see that the payload is the length that is reported by the client. So that's mistake number one, because it doesn't sanitize the user input and then just accepts the user input as correct. And afterwards over here, that's the second line. It allocates a buffer with that claimed size. So while it normally should be 4, maybe it is a lot more. Let's say like 500 on the example that we were working on. And then here's the mem copy, which then copies that critical information and then sends it to the user. So what is vulnerable? Basically, all websites that use those vulnerable versions of OpenSSL were vulnerable and then still up to date are. So which are versions 1.0.1 through 1.0.1f inclusive are vulnerable. And the vulnerability was introduced in December 2011. And again, the reason why this is such a unique attack is many confidential information was and could have been leaked, which are including but not limited to private keys, usernames and passwords, instant messages, emails, and business critical documentation. And one of the key things, which is even worse than usernames and passwords, is the private key leak, because the SSL depends on the authenticity and the private behavior of the private key, as the name implies, because the problem here is the attacker can access the private key of the server, and the attacker can behave like a server after with that private key, and then the damage is basically incalculable after that moment. And the impact of the bug, due to the really popular nature of OpenSSL, that is quite hard to do. But there is one source through Microsoft. In a 2014 survey that they've done, they found about 66 of the market share on all active sites on the internet uses Apache or Nginx, which used OpenSSL. And then with that information, estimates say about 500,000 websites were affected with this bug. And again, one of the concrete evidences I found was hackers stole 4.5 million patients' medical records from one of the US's largest hospital operator, Community Health Systems. Again, this can contain a lot of confidential information, such as address, or even worse, the social security number too. So the fix of the vulnerability, and I'm assuming this is where your affiliation comes in with the most, as you're working on Codenomicon, and this vulnerability was discovered by a team of security engineers at Codenomicon and Neil Mehta of Google Security. So the fix came on 7th of April 2014. It's about 3 years after the vulnerability. And the fix, as we can see here, is adding bound checking to user input, basically sanitizing it. And then the solution was approved by the open source community. So the code on the left here is the faulty one. As you can see, it just copies based on whatever the user tells the message length is, which was changed to a user bound checking, which here, if the length that the user providing doesn't make much sense or doesn't comply, it's just being discarded. However, the impacts still continue. Well, first of all, the e-week estimated the attack cost about $500 million. And the scary thing is, the attacks don't leave any trace. Based on a couple of sources I've looked at, they say they were both able to conduct an attack to their own server, and which did not leave any tracking, any trace at all. And the scary thing is, some people say there's still a lot of devices who use the non-updated OpenSSL version. And then since it was discovered in 2014, it's been more than 5 years now. And it's still a problem. And then this kind of scared me, because I really hoped and assumed that this was an ancient problem, but it doesn't seem to be that way. As you can see on an example from 2 years ago, there's still about 200,000 services that are vulnerable to Heartbleed. And I think one of the key reasons of this is, in a business-driven development world such as the one we are living in now, the developers aren't so great with keeping up with the updates. And it's the way to fix this vulnerability is fully up to the owner of the website, i.e. the developer, to update the OpenSSL to prevent this vulnerability. And although this is from 2 years ago, it could be safe to say that if the developers did not update their OpenSSL within 2 years, they might never do it at all. So the mistakes happened during the design. So the key thing was trusting the user input, which is really bad practice in terms of security, because we can't distinguish properly whether it's a good-willed user or a malicious one. And along with that, there is a lack of tests, because as we can see, the fix wasn't that complicated. It was just a simple bound checking. And most likely a couple of unit tests about corner cases could have shown the flaw in the design. Basically, they could have tried, the user provides a 5-letter word, but maybe they've written 50 by mistake. Let's see what happens. And then this could have shown that there's a problem waiting to arise with that. And then there are at least a couple of lessons to learn from this. First of all, one positive thing that came out of this is people became more aware of security issues after a high-profile library vulnerability such as this one. And that was also near the target breach. So hopefully this taught people that security is not an easy thing that could be left to future for many years to come. And for the developers of the technology such as like this, exhaustive testing and the security mentality is really key. Basically, following good practices of security development. And for the firms who use these technologies, don't expect the outside software, the code that you haven't written, to work with amazing security, because when the problem arises, if you use that library, it's going to be you, not the library, because the client doesn't care about what technology you use. They care about you, and then that could turn out to be a really major problem for the company you're working on. So this kind of also leads to a point that I want to make. It's something I found out about a couple of weeks ago, and that this really bothered me as well, because I've coded in JavaScript and basically Node and NPM. I coded in Node and then used a lot of NPM throughout my internship in summer. And what happened is there was a malicious code in an npm package. And as you probably know, npm is a really known package manager for Node.js, which is in turn a really popular framework of JavaScript, which is, again, one of the most popular programming languages of the world. And then the way that this problem arose was packages can be dependent on each other in Node. So an example is Express can use body parser, which can use debug, which can use something, and then this can go on for a while. And then the problem arises with a package called PureScript contained malicious code after an update. Although it wasn't anything to extract information or credit card or master key or something like that, it still showed that there can be inserted malicious code into the update. So you might not use PureScript directly, but the package you're using can be dependent on that. And PureScript got used about 2,000 times a week. And the lessons to learn from this is a big implication. Like you can just install a library to show pictures of cats to your client, but that library can end up stealing that credit card information. And then I thought this is quite similar to OpenSSL, because just because you haven't wrote that code, just because it's not your technology, doesn't mean you're not responsible with that. Because if a vulnerability occurs, it's going to be up to you to fix that. And this is kind of like a further reading, but I thought this is quite a major thing because JavaScript is one of the most popular programming languages and Node is specifically used for server software. And then the design of NPM seems to be inherently flawed in terms of security, which the link I shared talks more about this. And this still shows, although Heartbleed happened 5 years ago, while we hope that people learned a lot, but there's still a lot of major strides to be made. And here's the sources that I've used. The ones that I've took images out are from the left, and the ones that I did research on are from the right, which includes some of the code snippets as well. And also over here is your slides that I've looked at. Thank you. Thanks.